go quickly over some of the homeworks from 4.4, and this was about a basis. And so the first question was here, three vectors in R3, are they a basis? And the answer for this, the way to do this is very simple. What we need to do is make the matrix of these vectors, where we use them as columns, and then show that that matrix is invertible. And why is this? Well, let me quickly go over the reason why this is, so a quick review of why. So if these are the three vectors, what this is to be a basis means that if you take any vector v, so if v is a vector in R3, then this, you can write it as a linear combination of them. That means it lies in the span of these guys, but you can write it uniquely. There's a unique solution. x1, x2, x3. That's what it means to be a basis. And that unique solution we will call the coordinates. And so what does that mean then? Well, that means if you make the matrix of this, and so what's the matrix of this linear system equation? If you write this out as a linear system equation, what's the matrix? If you think a little bit about it, these are the matrix given by putting the vectors in there as columns. So that's often, you see, we almost always do this, right? We will write those vectors as columns in our matrix. Okay, and so what does it mean for a system of equations to have a unique solution? Well, that means that if you row reduce this matrix in the reduced form, you have to have no free variables, because free variables would give more solutions. So there can be only pivot variables. That means how does a reduced echelon form of a 3 by 3 matrix look like? If it has only pivots, it has to be the identity matrix. That means that A is invertible. That means the determinant of A is non-zero. So, quickly saying, unique solution. So to show, so the question is this a basis? So is this a basis? And the way to do that is to show that the determinant of A is non-zero. That's it. So we have to calculate the determinant, which is not so bad. So we're going to do this with our so 3, 2, 1, 1, 5, 4, minus 4, 6, 8. Okay, I have a 1 here that I can use as a pivot. So the row operations I'm going to do are row 1, replace that row 1 and subtract 3 times row 2 from it, and row 3, and I'm adding 4 times row 3 to it. Okay, using the pivot to get zeros in the rest of the first column. So what we get, so I'll do this with -3, so I get a 0 here. -15 plus 2 is -13. Why is this jumping? And -3, -12, that's -11. Get a 1, 5, 4. And now I multiply this with 4, so I get 0, 26, 16 plus 8 is 24. Okay, so what's the determinant? Well, let's be correct, although we only need to show it's non-zero, but this is a minus sign here, right? Because of plus, minus. And then we scratch out these two dies, so what's left is -13, -11, 26, 24. Now you can multiply this out and see it's non-zero. It's a little bit of bigger numbers. So sometimes if the numbers are big, I prefer, but I'm not saying you have to do that. So I'm going to show you, is try to factor out things. And I can factor out to 13 in the first column. So, and you remember, you can factor out any factor out of a column or a row. It doesn't matter. So if I do this here, I get a 1, -13. No, I'm factoring out 13. So -1, a 2 here. The negative is already original negative, right? And these two guys, okay, I don't see what to do here. I could even factor out an extra 2 in the bottom here, but let's now write down what we have. So with -13, we have -24 minus -22. That is plus 22. So we get -13 times -2, so we get 26. But what it matters is, as I said, it's non-zero. Therefore, we have a basis. Okay, that was easy. And so you do this for 4 by 4, 5 by 5, as long as you have the right amount. Because, of course, what you have to get is a square matrix. Okay. Now, how is question 12 is different, though. Question 13, sorry. Question 13. A, we have given three vectors, so I'm going to write them up again. V1 was, where are they? 1, 0, 0. V2 was 2, 2, 0. And V3 was 3, 3, 3. They were trying to be cute. Okay, so now we know, well, we don't know what is a basis. They tell us a basis. We will see. We'll see very shortly that why it's a basis. But the question is now, okay, we have given here a V. They pick something random, I'm assuming. This would be here 2 minus 1, 3. And then the question was, what are the coordinates of V in this basis? What does that mean? Well, it means V, we know that V can be written as a linear combination of these guys. Remember, that's what we were talking about, what it means to be a basis. Right? And remind you, this is what I was saying here, right? It's exactly this thing here. It has a unique solution, that's then the coordinates. And so that's what we have to do. We have to solve this equation. Now, how do you solve the equation? A linear system of equation like this? Well, it has a non-zero, it's a non-homogeneous one. Well, it's always the same. You make the matrix of the linear system of equations, which is given by putting these vectors as columns. So again, the columns here. 3, 3, 3. And then we do have also to add this as our augmented column. Right? If you would look if you would write down what this linear system of equation is, this would be the constants and that would be the last column. And now we have to row reduce. Well, we're almost in echelon form, except that this and this has to be a 1, so we have to do some divisions here. Row 2 divided by 2, row 3 divided by 3. So you see sometimes fractions are inevitable. So what we get is 1, 2, 3. We don't do anything with this one yet. 0, 1, 3 halves minus a half, 0, 0, 1, 1. Okay, dokie. So this is already our echelon form. And though, by the way, notice that we have 3 pivots and no free variables. So that proves that this actually was a basis, right? This means that this matrix, the first part here is an invertible matrix. Okay, but because we need to solve the system of equations, we need to go all the way to the reduced echelon form, which is the identity matrix. So in other words, we have to use this one to get these two guys 0. So this is what we call phase 2, right? In phase 2, we start from the bottom and work our way, I don't know what to say, back, we go from the bottom in the back to the front, right? Get zeros on top of all the ones. Okay, so we do row 1 minus 3 times row 3. We're working with this row, right? Because that's where the pivot is. And row 2 is row 2 minus 3.5 times row 3. So what we get, okay, so what I'm doing, I'm multiplying this to negative 3, so I get 1, 2, 0. Negative 3 plus 2 is negative 1. Right, yes. Okay. Yep, and then for row 2, I have to do now multiply with 3 halves. So there's 0, 1, 0. So minus 3 halves, minus a half is minus 4 halves, that's minus 2. And then finally 0, 0, 1. 1. Okay, the only thing that we need to get rid of is this guy, which we do by another row operation using this pivot. So row 1, replace row 1 minus 2 times row 2. This is always the row where the pivot is, at the back here. Okay, so we get 1, 0 times, so we do this times negative 2 and add, but that's just a 0. 4 minus 1, that's 3, 0, 1, 0, negative 2, 0, 0, 1, 1. So what does this now mean? If you write down what this means, remember this was a system in x1, x2, x3, right? This first thing means 1 times x1 plus 0 times x2 plus 0 times x3 is 3. So in other words, x1 is 3, and x2 is negative 2, and x3 is 1. So now if you want the coordinates of v is just 3, negative 2, 1. This is also a three numbers, right? We are in a 3-dimensional space, so we're going to have an x, a y, and a z coordinate. in this case, of course, with respect to a basis that is not a standard basis, right? So this is a skew basis that you can get. And we can now verify that this is true, right? So you could just plug in here. So what is it? 3, -2, 1. So no, that's mod, so 3 times that, -2, 1. Does it work out? Well, so this, if you add this up, we should get original vector. Okay, let's do this quickly. So 3 times 1 minus 4 plus 3, that's 6 minus 4, that's 2. Then I have 0 minus 4 plus 3, that's -1. And then 0, 0 plus 3 is 3. Okay, I didn't need, you don't need to do that, but I'm just showing you that it is correct. It's a good thing to do, because I must admit, the first time I did this myself, I made a mistake, and I luckily checked it and I saw it was wrong. So better to always check your answer if you have the time. Okay. Oh. Now 13b is kind of similar, right? And so I'm going to go rather quick on this one now. So in 13b we have a different system set, and I'm going to write them already. The first, the 3 vectors v1, v2, and v3 are now 1, 2, 3. -4, 5, 6, and 7, -8, 9, and the last one that we need, the v that we want to write as a linear combination, that is 5, -12, 3. I hope I covered it right here. I think I got it right. Okay. Okay, and so the same thing, right? Row operations, and I hope everybody sees why I'm doing this. I'm going to replace row 2 by 2 times row 1, and row 3 minus 3 times row 1. And this gives me 1, -4, 7, 5. So I multiply this with -2, so 0, 8, 13, -14 minus 8 is -16. No, what I'm saying, -14 minus 8 is -22. Right, -14, yes, -22. And then -10 minus 12 is -22 again. Oh, this is getting ugly, right? And then the other one is 0. So now we multiply with -3. 12 plus 6 is 18. -21 plus 9 is -12, right? Okay, and then -15 plus 3 is -12. Okay, yeah, this is getting a little bit ugly. Look, the book sometimes does these things. Let's now what you could do is try to get the 1 somehow in one way or the other. You see that the third row is divisible by 6, so you could do that. So okay, I'm going to do that. So the operation is row 3 replace that 1/6 of row 3. Okay, I'm going to be lazy and write just replace this 1 row here. That you can do, right? Because I'm not mixing anything. Okay. No, that doesn't help me much because it's still not 1, and we still have the 13 there. So I don't know what you want to do here. I could multiply row 3 4 times and subtract it from the 2. I'm going to do this because I really don't like fractions. But what you should do, what you normally would do, is just divide one of them. Either this one, that's the least work if you divide it by 13, but you get the biggest fraction. But I'm going to be lazy, and what I'm going to do is I'm going to do row 2 minus 4 times row 3. Why do I do this? Because look what I get then. Look, watch the magic happen now. I get, I'm multiplying this with -4, right? So I get 0. -12 plus 13, that's the one I wanted. 8 minus 22 is -14, and 8 minus 22, well, it's -14, same thing. 0, 3, -2, -2. See, that's how I don't have to deal with the fraction, at least not now. Probably at some point I have. So, making this one 0, that is row 3 minus 3 times row 2. 1, negative 4, 7, 5, 0, 1, negative 14, negative 14, 0, 0, so I'm multiplying this with negative 3. That's plus 42 minus 2, that's 40 and 40. The good thing is now I can divide row 3, let me do this in red, okay, so row 3 divided by 40, okay, again I'm do this simple like that. If you do this on a test, be careful that I can read everything still, right? Okay. We got our echelon form, and again it shows that there are no pivot variable, no free variables. Everything is pivot variables, but we need to make things 0. So to get these two guys 0 using this pivot, that's row 3. So the row operations are row 2 minus replace row 1. Replace row 1 by row 1 minus 7 times row 3, and row 2 plus 14 times row 3. Okay, so I get 0, no, not 0, 1, 1, negative 4, so I'm multiplying this with negative 7, so that's 0, so negative 7 plus 5 is negative 2, and now I'm multiplying this with 14, so I get 0, 1, 0, 0, and then I have 0, 0, 1, 1, right? Yes. Good. Only one thing left to do. That's the row operation row 1 plus 4 times row 2. I'm using this pivot in row 2. So I get 1, 0, 0. So I'm multiplying this with 4 and add up there, but that's nothing happens. Minus 2, 0, 1, 0, 0, 0, 0, 1, 1. And so what we get is here, the solution is the coordinates are just the last column, right? Minus 2, 0, 1. And again, we could check this if we do minus 2 times, where are we here? If I do minus 2 times this one, plus, what was the other one? Plus 1 times this one, I get what I need. Okay, I'll leave it up to you to check that, okay? And by the way, notice what this means. This means that we have a coordinate 0 here. That means that actually this vector doesn't play a role. So what we actually showed is that if you look at the span of these two vectors, which they span a plane, not the whole thing, this vector that we had, this fourth vector here, is actually already in that plane. That's what that means. But again, I'm just saying that for extra information. All right, that's it.